Dr. Glazer, you think you're going to put one of those on the test?
Yeah.
No.
I mean, there's a good chance. Okay. Let me take a drink of water. Any questions so far? Yes?
For that second equation, the capacitor equation, is the E squared, is that the electric field?
That's the electric field inside a capacitor, yeah. Right, so if you have some parallel plate capacitor like this, okay, and you have some electric field inside, that's E, okay. The energy stored inside is proportional to E squared. It's also proportional to V squared. So if you know the electric field inside, or you know the voltage across this capacitor, right, which you often know the voltage across the capacitor, you can use those equations right there to relate, well, first of all, V and E, or V or E to the energy stored inside of that capacitor. Okay. Are we on to the next chapter yet? I don't remember.
I think we're on chapter 33.
33. Are we even on chapter 33 yet? I think we're on chapter 32 right now, right?
Yeah. I think we're on 30, right? Like what we just did.
I think this was all the end of this chapter.
Can we start at chapter like 3?
Was that?
Can we start at chapter 3?
Chapter 3? You guys remember what chapter 3 was? No?
Laws or something.
It was vectors. Take a little refresher on vectors.
Please.
Okay.
That's the line with an arrow on it, right?
That's pretty much the end of this chapter. I don't think I have anything else from chapter 29. Chapter 29 is a big chapter. It had a lot of stuff. Chapter 30, not so big. Chapter 30 was all about current. So the origins of current and how to calculate current from the electron current to the current that we use in circuits. Okay. Now the first thing was what causes current? Okay, you guys remember what causes current? What's that? Yeah, you guys have like a, it's not, I mean, yes, ultimately it is, but like a physical thing. Voltage is more of a whimsical thing, right? What do the charges do? What property of the charges? Move, yeah, but charges don't move themselves. There's something that has to do with charge. It is an electric field. Yeah, an electric field moves the charges, but what causes the electric field? Okay, well,
Separation of charge.
it's sort of separation of charge. What does that imply? If I have, but see, that's weird, right? Because if I have some battery and it looks like this, okay, and it has two terminals, and they come out in these wires and they do whatever they do, and then I put some light bulb across it over here, right? What does the electric field over here have to do with these, with this potential difference across this battery here? What's causing that? That's the question. What causes current to flow through the wire?
Not lack of resistance.
No.
Non-uniform surface charge.
Non-uniform surface charge. Everybody, round of applause. And he memorized that. Okay, he didn't even use his notes. Non-uniform surface charge. That's exactly right. That's the thing. So it turns out that if you have some chunk of wire, like this, on that wire, if you have some potential difference, it causes some non-uniform surface charge. So if you take some little surface charge density over here, let's say this has a lot of positive charge on it, okay? So we have a large amount of positive charge over there, right? Because we are right next to the positive terminal of the battery. So we got a big positive charge. That's what's going on over here. Now in the next chunk right here, we have some, maybe we have some smaller amount of positive charge like this, right? Just a couple of charges. Well, in that case, we're going to have some, in this point in the middle of the wire, we're going to have some big charge, or sorry, some big electric field in that direction due to this ring. I'll call this ring A. So that's E sub A. It's a big electric field in that direction. And we have a smaller electric field in that direction from ring B. Okay? And that causes a net electric field in this direction. Need a bigger piece of chalk. Okay, and the same thing all along the wire. Anytime there's this gradient of surface charge, it causes there to be an electric field in the wire, which then cause any free electrons inside of the wire to flow down the wire, and that's why we have current. Okay, which brings me to electron current. Now this chapter was a weird chapter. It just throws a lot of definitions at you, and they'll probably all be on the equation sheet. And the best strategy is just to know what each of them are, what all the quantities are. And this chapter is particularly good fodder for conceptual questions. I can ask you, what, if I heat up a material, what happens to the mean collision time? That would be tau, right? Well, we'll get there in a second. So electron current that's this. IE equals N sub E times delta V times, oh sorry, that's not a delta, that's an A. I can't read my own writing. A times V sub D. Okay, that's the electron current. The best thing to do is just to know what each of these things are. Electron current is how many electrons you have flowing through a wire per second. Now N sub E, that's the free electron density, and it depends on the material. A, that's a cross-sectional area of your wire. Okay, and V sub D, that is the drift velocity. Okay, so I can ask you things about the free electron's density and how that affects the electron current, the drift velocity, and the cross-sectional area of the wire in various forms. I can show you different geometries and ask you which one is going to have a larger electron current. Okay, these are all things that I could ask. The other thing, right, is this idea that electron current, what's the thing that slows down electron current? Why is there resistance in a wire? Because of collisions, right? And if you look at the path of any electron, it looks something like this. This is velocity, this is distance, I think that's what it was. And the velocity, it increases like this. It goes down. I think this is distance. Better make sure. Well, it's fine for now. And then it goes up like this again, and then a hit makes a collision, and it gets knocked back. Okay, well this time between collisions right here, that is this tau. That is the mean collision time, or the average time between collisions, and it determines how fast these electrons make it through the wire is going to determine the resistivity of the wire and the conductivity of the wire. So it turns out that this is some important quantity. The average velocity, which is something like this, right? Something slower than this maximum velocity, but not zero, and it's going to be in the positive direction. That's our v sub d. That's the drift velocity, and it's the average velocity of an electron through some wire. Now, along with this, we get I sub e. That's equal to n sub e. That's the free density of electrons, or free electron density, times E, that's the charge of an electron, times tau, times A over the mass of an electron. That is also equal to the electron current right there. Now this one has a tau in it, okay? So it tells you something about the mean collision time and the current density. And there's a bunch of other equations in this. I'll probably throw them all on the equation sheet, and you can use them at your leisure. Because a test, of course, is a leisure activity. Yes?
In the note,